maximum gain amplifiers. My name is Steve Ellingson. Here's an overview of this lecture. First, I'm going to remind you about design strategy for small signal transistor amplifiers. Then we're going to jump right into an example, and this will be the design of a maximum gain transistor amplifier for an RF application. So in this lecture, we're going to be putting together all the ideas that we have assembled to this point in the course, and we're going to start using them. So this is the beginning of a real practical design. So to remind you, here is a synopsis of the problem in the format that we're going to try to solve it. So the idea is that we have some two-port device, and in this case it's going to be a transistor. This will be the gain device, and we'll define it as a two-port, and as a two-port it will have S parameters. And then we're going to choose input and output matches that present to the transistor impedances which achieve the goals that we seek. In this case, the goal is going to be maximizing gain, so we're going to use simultaneous conjugate matching. In other applications and in future lectures, we will have other goals or other combinations of goals which will lead to different impedances. In any event, here I'm reminding you about the nomenclature that we use. For example, Zin will typically be 50 ohms. It will be in this design problem, and it is in many RF problems, but it could be something different, and the techniques will still work. But here it's 50 ohms. Z out is 50 ohms. I use the subscript O here to distinguish it from another place where we're interested in the output. So just to be clear about that. And remember that we commonly use reflection coefficients as surrogates for impedances. So this is the reflection coefficient looking into the input, and it's the one that corresponds to 50 ohms. And similarly, looking in this direction into the IMN, we are going to try to achieve some source impedance, Z sub S, and it too has a corresponding reflection coefficient, gamma sub S. And typically we find gamma sub S and then convert it to Z sub S. We defined the embedded input impedance, gamma sub in. This is the impedance looking into the two-port, in this case the transistor, when it's terminated by the OMN, and the OMN is terminated into the design output impedance. Similarly, we have the embedded output reflection coefficient, which is a reflection coefficient we see looking into the output of the two-port, representing the transistor, when the input has the IMN, and the IMN is terminated into the proper impedance. And then we have similar quantities for the OMN, for the output impedance network. So this is how the problem is set up. So here's our example. Now for this example, we will continue from a previous example that we started when we talked about biasing. So this is a bipolar transistor, and in that earlier example, the transistor had a beta in the range of 60 to 130, which will not appear in the RF design, but just to remind you what the problem was. We selected a bias point of 5 milliamps and a supply voltage of 8 volts. And we designed a self-bias arrangement, finding that the collector resistor should be a 1.47 kiloohms, and that the base bias resistor should be somewhere between 100 ohms and 10 kiloohms, depending on the trade-off between insensitivity to beta and power consumption. And then we had these blocking caps here to remind us that we might have an issue with DC running out the input or running out the output. And then we have these components here, which are about RF DC isolation, and we kind of left those as to be determined, because who knows, in the RF design we may find something that suggests values for these. Even though they're part of the DC bias, they might play a role in the RF design, and I'll tell you they do. Now continuing, we want to do an RF design. And in this RF design, we want maximum TPG, We want to achieve it at 25 megahertz. That's the design frequency. And we wish for the input and output impedances to be 50 ohms. And also the reference impedance is going to be 50 ohms. So the S parameters we are about to give are with respect to a reference impedance, which is 50 ohms. And 50 ohms also happens to be the input and output impedance. So here's our S parameters. These S parameters would correspond to the bias point that we have selected here and to the frequency we have selected here. So this is a given in this problem. So here are the steps. First, determine stability. Whenever you do an amplifier design, you might as well do this first because you want to know what you're starting with. Hopefully it's unconditionally stable. If it's not, then you know you're going to have to do some more work, and you should be aware of that going into the problem. If it's unconditionally stable, you might as well check the maximum available gain as well. After all, in this case, we're doing max gain design. The maximum available gain is the maximum gain we should be able to get out of this. The technique for getting maximum gain, as we discussed in a previous lecture, is simultaneous conjugate matching, or abbreviated here, SCM. Once we know what the appropriate reflection coefficients are for simultaneous conjugate matching, then we're ready to solve the problem of synthesizing the input matching network and the output matching network. And these are simply impedance matching circuits of the type that we have already worked out in Chapter 9. The final step is tying all this together. We're going to have impedance matching networks for RF. We're going to have a bias circuit for DC. Somehow we're going to have to make all this stuff play together. So step 4 is going to be bias circuit integration. Really the first time we've directly confronted this, although I've given you lots of clues up to this point that we would be confronting this problem. Okay, step 1, determine stability. So as usual, we compute the delta parameter. We find that it has a magnitude of 0.06. That's good news. We calculate the roulette stability metric, K, and we find that that has a value of about 2, also good news. So since the magnitude of delta is less than 1, the magnitude of K is greater than 1. This is unconditionally stable as long as our source and load impedances are well behaved, and they certainly will be in this case by design. So since it's unconditionally stable, simultaneous conjugate matching solution is guaranteed to be stable, as well as yielding maximum gain. So this design should be relatively straightforward because we don't have to worry about stability. So continuing, we might as well check the maximum available gain, the MAG. And since this is unconditionally stable, we can use this expression for MAG. We've already computed K, and we've got the S parameters. We find that the MAG is 17.2 dB. And this should be the TPG if we determine the simultaneous conjugate matching input and output reflection coefficients correctly. So this gives us a valuable diagnostic. Okay, step 2, compute the simultaneous conjugate match. That consists of computing the desired source and load reflection coefficients. And we worked out expressions for those in a previous lecture. I called them gamma sub S max and gamma sub L max to indicate that they were the values of those parameters that gave us the maximum gain solution. And we had equations that looked like this. And in this case, when we work through all the parameters, we find this value as gamma sub S that we need, and this value is gamma sub L that we need. Now we check the answer. The way we can do that is to invoke the general expression for transducer power gain, for TPG. This is in terms of gamma sub S, gamma sub L, and various S parameters. We know what the S parameters are. We just calculated gamma sub S and gamma sub L. If we make the substitution and then compute the transducer power gain using this formula, we find that we get 17.2 dB, which is in fact the maximum available gain that we just calculated. So far, so good. Okay, now step 2. The corresponding input and output impedances for simultaneous conjugate matching. Keep in mind, what we have identified at this point is this value, gamma sub s, and this value, gamma sub L. These are the values that we have just computed. We need to convert these into impedances, Z sub s and Z sub L. Easily done. Here we go. Z sub s is the reference impedance against which the S parameters were computed, 1 plus gamma sub s over 1 minus gamma sub s, and we find that this is the source impedance looking into the output of the IMN that we need in this case. Note that it's complex. So we see that the IMN is going to be a complex to real matching network. Similarly, we can compute the load impedance, Z sub L, and we find that that is this value, 82.4 plus J 63.5 ohms. Again, it's complex, so the OMN is going to be a complex to real matching network. So let's start with the IMN. So here is a picture of the IMN. We know that this is 50 ohms. That was a given. We just computed this, Z sub S. So we need to figure out what the network is going to look like. So first, I'm going to make a note here. It is very easy to get confused at this point, because what has happened is we've computed the value looking in this way. But in Chapter 9, when we were working out impedance matching networks, we were talking about matching impedances looking in this direction to an impedance looking in this direction, right? So in terms of the Chapter 9 analysis, what we have computed here should be conjugated because we want to be looking this way. That's Z sub S conjugate. So just be careful about this. Make sure you understand in what directions the impedances you're looking for should appear. Okay, so now let's do this assuming we want discrete two-component L matching, right? In other words, we're going to use two reactances, and we have a procedure for doing that. And this is a reasonable thing to choose for 25 megahertz. It's quite a low frequency, and I don't think anybody would propose using a strip line design here. At least I can't think of a reason why you would do that. So this is the technique to go for. When we invoke the methodology that we've developed for this, we find that there's a series first L match, which gives two solutions. And we find there's a parallel first match, which yields no solutions. So in other words, no parallel match. So there's just two series first solutions in this case. And here they are. I am not going to work through the details of this calculation for you because we've done this previously and the technique is being applied the same way here. However, you should make sure you can synthesize these two IMN networks. This will also confirm this business of ZS versus ZS conjugate and make sure you're doing everything right. Also, you can check that these are correct by evaluating these circuits. In other words, we know we want to see Z sub S conjugate looking this way. So this way we see Z sub S conjugate in parallel with this inductor, and then we see that previous impedance in parallel with this capacitor, and that should be Z sub I, in other words 50 ohms. And then you can have confidence that you did this business right. Similarly, we have another series first solution over here, and those are the component values. Okay, so now we have to decide which one of these two input matching networks to use. We look at the circuit that we're starting with that has the bias in it already, and we see that there's really no particular advantage in either input network matching solution. The component values here are all reasonable. We don't have any guideline on whether we should be low pass or high pass. There perhaps is some issue about how you could get to these values using the smallest number of standard values, and I think that's a perfectly reasonable basis for selecting. But here, just to keep it simple, I'm just going to arbitrarily choose one, and I'm going to arbitrarily choose the one with the low pass response, this one. Now I would like to integrate that into this circuit that I'm starting with. But first I want to do the output matching network as well. So here's output matching network. Once again, I'm showing the relationships here, 50 ohms looking out this way, gamma sub L conjugate looking this way, because gamma sub L is defined to be into the OMN. So just keep this in mind when you do the synthesis of that matching network. Here are the solutions. Once again, you should work these out on your own. It's excellent practice to make sure you can get these same results, and then to confirm that they're correct. Again, you can look here and know that that's Z sub L conjugate. You can look here, that's Z sub L conjugate in parallel with that capacitor. That's that previous value in series with that inductor, and that should be equal to 50 ohms. So you should be able to do that kind of check on the networks that you synthesize. So now we go back to the original circuit with our two candidate output matching networks, and we see if there's any way that we can pick one. In this case, the component values are all reasonable, nothing to fear here in any of these values. However, there is a basis for which I have a preference, and in fact I have a preference for this version, this solution to the output matching network. The reason is, first, this capacitor here, this 100 picofarad capacitor, can double as this capacitor here. Here, this capacitor is being used as a DC block. Here, this capacitor is being used as part of the impedance matching network, but there's no reason why I can't use the same capacitor for both. Furthermore, this inductor here can serve as this inductor here. Now, that might seem a little bit surprising to you at first, but look what's happening here. This node here corresponds to this node here. This node here is not necessarily ground. This is just the datum in the RF signal. So as long as this goes to ground at RF, I'm okay. Well, I get that if I put that little capacitor there. That's a bypass capacitor. So in this case, I like this solution because it maps very nicely to what I already have decided for my bias network. So here it is after I put it all together. Here's my input matching network, and here is my output matching network. Notice I've chosen values for capacitors. In this case, I've chosen 0.01 microfarads for both of these capacitors. And the reason is simply that this is a very commonly appearing value. We know that this value is not going to be particularly sensitive. We just need it to be in a certain order of magnitude. 0.01 microfarads at 25 megahertz has a magnitude of 0.6 ohms reactance. So 0.6 ohm reactance compared to 50 ohms here hardly matters, so that's adequate. And 0.6 ohms here will be a nice short to ground, approximately, for the RF signal. So in this case, I've chosen that. And I've chosen to make them the same just to simplify the bill of materials. I've also chosen now R sub 1. Again, arbitrarily, I just chose a mid-range value. Remember, we had choice between over a very large range, several orders of magnitude. I just chose somewhere in the middle, 1 kiloohms. As you recall from the previous lecture where we designed that bias circuit, it just is not very sensitive to this. And 1 kilo ohm is a fairly common value. So just to conclude the design, I've made a selection mid-range. And anywhere in here, if I wanted to fiddle with the values, I have the freedom to do that. And in fact, a large fraction of any practical design problem is not in getting to this point, but rather in refining the values now to optimize bills of material, to make the component count minimized, to get the best fit to existing values, and so on. A recommended final check here. Make sure that you didn't do anything that will short circuit or interrupt the bias circuit design. We have integrated the input matching network and the output matching network into this design. We should look carefully and make sure that we haven't done something that's going to create a short for the DC bias, for example, or an undesirable open circuit or something of that nature. So for example, here at DC, this is a short circuit, this is an open circuit. So at DC, the IMN just disappears as we need it to. And the output, this is a short circuit, this is an open circuit. Once again, the bias is doing the right thing. This concludes this lecture on design of maximum gain amplifiers.